if you don't have your lab textbook yet, please reach out to me. I will post what I can that's freely available. And then if you send me a note, I could maybe share a couple of pages from the book as well until you get your own book. But I did have a question about how important it was to get the lab book. And this quarter, it's going to be pretty important because we really have to focus on the theory and the tests that we're going to do on unknowns. It's going to be really heavily in the book. Today, I just want to do a real quick, maybe half-hour talking, and then have you guys pair up and talk about your samples that I'm going to assign you. And for anyone who's not here, I'll have to take attendance real quick and see who's not here, but I'll have to get them their samples as well. Okay, so that's the plan for today. So let's start with a little bit of notes here and the basic idea of experiment 55, which relies on understanding how to purify samples. So I'm going to share my screen when I can find that. And then we're going to look at some ideas here. For those of you, again, who don't have the textbook, I found a free online resource through Chem Libre Text, Chemistry Libre Texts, or chem.libretexts.org. I posted this on our website under the pre-lab assignment. So please feel free to look at the free articles about recrystallization and extraction. And they talk about choosing solvents here, and they talk about the theory of how it works. So that might be helpful if you haven't had OChem in a while. Okay, so just a little bit of overview, and then we'll talk about some of the worksheets and things. So first of all, recrystallization, that generally is when you have the purification method, okay? And generally, what you're trying to do is purify based on slight differences in polarity and solubility. Of course, polarity and solubility are closely tied together, right? If something is pretty polar, it's going to be pretty soluble in something that's polar. Like dissolves like. So usually what we're talking about is having two compounds where they may look very similar to each other, but they are a little bit different. And I'm not sure if I think I sent out the link from office hours earlier this week, where I talked with some students about, thinking about compounds that look similar, but there is a difference in their polarity. So I'll just write an example here, which I think is from my example in the video, if you're able to watch that. So here's benzyl, okay? And then here's maybe a similar looking compound. Certainly it's going to have the dispersion forces to help bond this to benzyl. They're probably going to be miscible in the same kind of solvent. So I would probably be sure that they would definitely dissolve in something like hexane because they're very nonpolar from these aromatic rings. But being soluble in hexane, they're going to be too soluble in hexane. So if I'm trying to separate them, I want to take advantage of the fact that this one has this additional polarity from the C double bond O carbonyl groups. So I would probably want to choose a solvent that's intermediately polar to take advantage of something that's polar there. And really a very common solvent to use would be something like ethanol or methanol. And you guys know from experiment 3 that talks about recrystallization that we did test out a lot of different solvents. We tested water, which is very polar. We tested ethanol or methanol, which is intermediately polar, because it has the carbon chains, but it also has the OH group. So it got polar and nonpolar. And then we tested out like hexane or methylene chloride or ether. That's pretty nonpolar. So an ether is sort of in the middle ground, actually, because of the oxygen, it's a little bit polar, but because the carbons, it's not, and the symmetry, it's not. So there's this whole spectrum, right? So on the polar side, we had water, then we have methanol, then we have ethanol, then we have like acetone, we have ether, you know, these guys. And you start to get more and more nonpolar. You have methylene chloride, which is a little bit polar also because of the chlorines. And then you have on the very end here, you have like hexanes or benzene, you know, very nonpolar things. So the idea is in recrystallization, you don't want to be out on the edges because you probably won't dissolve these at all in water, but they dissolve too much in these solvents. And so that's an idea that you learned in experiment 3, that you want to stick somewhere in the middle so that when it's hot, it dissolves both of these really well. And then when it cools down, one of them likes to dissolve more and the other doesn't. So when the solvent is cold, that's when you want to see the difference in solubility. So this, I'll just write that real quick then. So the way that this separates is that when the solvent is hot, when solvent is hot, and I'm sorry about my writing here, both are soluble, but when it cools, one precipitates. And of course, for it to precipitate, they have to be solid, right, when they're not dissolved. Okay, so that is really good for solids, to dissolve them and have that difference at different temperatures of the solvent. Any questions on anything that I said or anything about recrystallization in general? Okay, and just as an additional visual, because I know you guys are
real
visual.
Quick, Jenny.
Sure.
I can't read the serial killer handwriting.
Yeah, I know, I'm sorry.
What does it say just to the right of acetone?
Acetone ether.
Ether, okay.
I will be a serial killer by the end of this quarter.
Who you telling?
Okay, because I'm like sitting in Zoom for like 8 hours a day, like you guys are, I'm sure. We're all gonna be serial killers. All right, so yeah, so see, I'm drawing the structure so that you can see that, yeah, I mean, as you look at these guys, you know, you can see the polarities changing. And if I'm trying to match the polarity of this, you know, oh my goodness, I would see this might be a good candidate, right? So this and acetone might work pretty well because they're going to be miscible with each other, or this will be soluble in this. Maybe too soluble though, so, or, you know, maybe I want to choose something. Yeah, well, maybe it might work, and then maybe this might work also. So how would you really know? I mean, I think from experience, you just have to try it and you have to see what actually happens. In the workbook, well, in the Merck Index or in the CDC handbook, you can look up sort of whether it's soluble or not. But before I show you that, you can see you want to match some parts of that, but you also want it to be somewhat nonpolar for these guys. See, so that's also important, is to make sure that you are accounting for, you know, sort of the nonpolar parts as well. Okay, so this is intermediately polar, this is intermediately polar. So that's a really good prediction that when these two dissolve in hot ethanol, this guy, or hot acetone, this guy, this will probably attract itself more, and then this won't be as attracted to this, right? Because it's a little bit more nonpolar. So hopefully this might crash out first. So maybe this will be the, when you filter it, let me draw that, or try to, okay, when you filter, you know, and so you've got all these things in whatever, the vacuum, okay? So you've got like these two dissolved in acetone. You know that these two will be more soluble together. So what do you guys think will be at the top here? When you take these hot liquids, you cool them down, you get crystals. Which of these, the one on the left or the one on the right, is going to be at the top?
The one on the left. Sorry, the one on the right, I think.
Yeah, that's right. So these will be more soluble. So yeah, that will be in the mother liquor, what we call the mother liquor. It'll go through. And then the stuff on the top will probably be the stuff that's not as soluble. Thanks, Manuela. That's right. Okay, so the benzyl. Okay, so that's for you to sort of predict as you're doing this lab today and this week. A couple of notes then. What I would do is, you know, when I was a student, we had to go to the library and we had to use the Merck Index. But you guys are lucky. A lot of the information is online. And in fact, in my experience, Wikipedia is actually okay at just reporting the facts as far as chemical information goes, although you do have to be careful still, you know, because there's with chemical physical properties and chemical properties, there are slight differences. Like, you know, I know chemists who will like argue over the 4th decimal point of the molar mass of, you know, some element that nobody cares about. Okay, they are really annoying people. There'll be like long email threads like, well, where did you get that from? I got mine from the IUPAC conference of 1978. And you're just like, oh my God. They're funny though. I love those people too. So anyway, you will see some solubility data. And what I did was I just Google searched fluorine solubility, solubility in ethanol, you know, or solubility period, you know, just whatever. And I was able to find some info here. You could see fluorine, which has this structure here. You guys have used it before in experiment 3. Fluorine is soluble in carbon disulfide, ether, benzene, hot alcohol, pyridine, toluene, blah, blah, blah. So see, they're telling you what it's soluble in. The fact that they said hot alcohol is a good sign, because that means maybe it's not so soluble in cold ethanol, and then you have that difference in temperature. One of the videos I linked in the pre-lab, they sort of gave you some data about benzoic acid is this soluble in hot ethanol and this soluble in cold ethanol or water. So that's very important if you have any inkling that things have a different solubility, like drastically different in different temperatures, at different temperatures. Okay, let's move on then. The next thing is extraction. So in liquid extraction, the idea there, liquid extraction, first of all, the liquids we're talking about are usually the solvent liquids, okay? So the liquid extraction, the solvents are the 2 liquids. You have a polar solvent like water or aqueous solutions versus a nonpolar solvent. And the 2 do not mix together. They're immiscible with each other. Usually ether, gosh, anything ether and below, right? Because acetone, ethanol, and methanol all dissolve with water to a great extent, almost completely. So ether, methylene chloride is another one we used, or dichloromethane, DCM, hexane, you know, things like that that are very nonpolar, they're not going to dissolve or be mixed with water. Okay, so with the 2 liquids, then you want your solid mixture with multiple compounds in it to be distributed in the 2 different layers. Now you guys know from experience, like when we did caffeine is somewhat polar, so some of it goes in the polar layer, and the other, most of it though, goes in the organic layer because it's fairly nonpolar. So you will see that there is this difference in, you will see that it's distributed in both layers to some extent, but you want most of it to be in one versus the other. Okay, so for example, when you take like, usually we use a separatory funnel. So, and I don't know, some of you guys used one last quarter, and some of you guys stayed away from it because sometimes the valve opens up and it's just a real pain to deal with. Okay, so here's my separatory funnel. or you could use a centrifuge tube or a test tube and see the two different layers. Okay, so here in this separatory funnel, I've got my liquid in here with the two layers. Okay, so here's one layer, and that, let's call that well, it depends on what solvent, right? How do I know what's on the top and what's on the bottom? Okay, so it depends on what the two solvents are. Do you guys remember who's on the top if we have a mixture of methylene chloride and water? Do you guys remember who's the top layer? Whoa, there's my retirement stuff. Okay, H2O. Let's say I have two layers, methylene chloride and water. Do you guys know which one is going to be on the top and which one will be on the bottom?
The organic one will be on the top. The water will be on the bottom.
Actually, what would
I
it
think-
depend on?
Is it the water that will be in the top since it's lighter, maybe?
Right, exactly, Maria. It's the density.
Oh,
And
yeah.
in this case, it turns out, so most of the time, the density of the organic layer that you're used to is on the top. Usually you use ether, and that's on the top. But methylene chloride is different. Because of the chlorines, it makes it more dense. So methylene chloride will be on the bottom. Okay, so let's make a note of that. So methylene chloride will be on the bottom. And a lot of times you can tell just by looking at the density. And water will be on the top. But compare that to if you were to use ether, so diethyl ether and water, it'll be reversed. This will be on top and this will be on bottom. So you really just have to predict based on density. But of course, if you have a lot of stuff dissolved in the solvent, that changes its density and you can have a reversal as well. Okay, so just FYI, this is how you know. Okay, so let's say that we have water on the top layer and methylene chloride will be on the bottom layer, okay? And so then this separatory funnel, you can open the valve and the bottom will drain out, and then you close the valve as this layer moves down and gets ready to go through. You don't want it to go through. All right, so let's say that we end up then with our methylene chloride, which has our organic stuff in it. Okay, so our very nonpolar stuff will be in the organic layer, nonpolar. And then our polar stuff and our salts and whatever else, that will be in the aqueous layer. So I'll make a little note here, organic layer, and this is the aqueous layer. Okay, so now, usually we care about the organic stuff, right? Hence organic chemistry. So all these organic molecules in here, we're of course going to lose some of that because, you know, a small amount of that will dissolve in the aqueous layer as well, but most of it should be down here. So there's a difference in solubility that creates this situation here. Okay, so now that we have this, what do I do with it? Do you guys remember, like procedural wise? I don't want this liquid, I just want the solid.
Extraction?
Oh, so I did the extraction here.
Evaporate it.
Right.
Evaporate it.
Dry it.
Yes, that's right. So I dry it first. So what can I use to dry this?
Boiling.
Well, I don't have a lot of water there, but I have
The
some.
water bath and the nitrous spray.
Yeah, but before that, I have a drying agent.
Oh,
And
you got to
Yeah.
put that.
sodium
Snow
sulfate.
globe.
Right, snow globe, Na2SO4. It's anhydrous sodium sulfate, a white salt that you shovel in your tube there, and then you wait and let it absorb and form a hydrate crystal. It absorbs the invisible water that you cannot see in here. And maybe some of you guys can see it because you didn't stop this valve in time, okay? All right. Now, one more thing. Sometimes we do multiple extractions. Do you know what I'm talking about? Can anyone explain what that's all about? What do I mean by extract it again or do a second extraction?
That's where you add more.
organic layer.
Oh, sorry. Go ahead. Was that Tony?
You add more methylene chloride.
Great. Okay. So when you drain this bottom layer you're going to get aqueous layer. But remember I told you there's a little bit of dissolved organic stuff in here that you want. So you would add methylene chloride to here again and have this stuff move into the bottom layer, thereby increasing your yield or your recovery, I mean. Okay, and then you're going to drain it again and get a second batch. Then you would combine those batches. So I would say do at least 2 extractions to try to maximize your recovery. And then you would combine all those, you would add sodium sulfate crystal, and let's show that with this green stuff here. Okay, let's say that's the sodium sulfate drying agent. That's gonna soak up any water droplets and the crystals swell up. And then you check it out and you see if the crystals have gotten bigger. If they have, that means there might still be water that you're missing out on, so you add more. And then you get to a point where you can evaporate the solvent. And that's where some of you guys said you boil it. Okay, so you evaporate the solvent and then you should theoretically end up with that one compound. And hopefully your impurities have stayed in the aqueous layer. So that's the idea there. Okay, so evaporate the solvent. And so of course we can't really use solids that, most solids don't easily evaporate anyway, right? They usually melt and then you can evaporate them. But just in case you know, these are not very volatile, right? So these are solid crystals. Okay, so otherwise we'd be in trouble when we evaporate. Okay, so the solvent is easily evaporated. Usually we pick solvents like these, tend to evaporate at like 35 degrees Celsius approximately. So, okay, that's the basic idea. And you guys can see then that there are 2 techniques we covered. When do you use one and when do you use the other? So did anyone figure that out?
Recrystallization should be used for intermediately polar molecules.
Mm-hmm.
And then the liquid extraction is when you're dealing with non-polar and polar molecules.
Yeah, I like that a lot, Tony. That's right. So if the difference in polarity of the compounds you're separating is great enough that you know a significant amount will go in the aqueous or organic layer, there's more of a polarization, right? Either you're very nonpolar and polar, then this would work really well. Or if you're intermediately polar and you're mixed with something really similar in polarity, where it would be harder to say this would go in the water layer and this would go in the organic layer, probably they would both go in the organic layer. Then you need to use recrystallization. So recrystallization is more of a subtle difference in polarity, whereas this is more extreme. For example, what kinds of things might this work for? When we did liquid extraction, usually what we did was we took intermediately polar molecules like benzoic acid, and we made it more polar than it currently is. Right now, I would say it's intermediately polar because you have this polar part right here. I keep doing that. We have this polar part of the carboxylic acid and the non-polar part of the ring. And so it's intermediately polar. But because the benzene ring is such a non-polar force, it's gonna make this pretty non-polar overall, actually. So do you guys remember that I can actually take advantage of a feature of this, a chemical property of this, to make it more polar? Do you remember what I need to add to make it more polar?
Should add like a, I'm sorry.
What do you guys think? Yeah, Manuela, go ahead.
I just think you add acid.
Close. This is an acid. So what should I add?
Base.
A base, right. So this is an acid, and what I'll do is I'll add a base. And together it will react and force this to become more polar by becoming charged. And this charged part right here makes this really attracted to water. And so this will become really polar and then you'll get that difference in polarity between the two. Yeah, you know, you'll get this wanting to go in the water layer at a much greater extent. Okay, so the key to this then is that if you have an organic acid, or also if you have an organic base, so let's draw an example of an organic base. That would be, what do you guys think? What kind of functional group?
Amine.
An amine, exactly. So let's say an organic base version of this might be an amine. And it doesn't have to be aromatic. I'm just choosing that to match benzoic acid. But basically, I have okay, I have this, okay, and this right here is my basic part. So when you see an amine or a carboxylic acid, you know that you have this extraction capability. Okay, so what would I add here? Would I add NaOH again?
No, just H.
Mm-hmm.
Oh, sorry, acid.
Yeah, acid, right? So I might, oh, darn it, I keep doing that. Okay, I might want to add HCl or H plus in some way, right? So I'm gonna grab that way. Okay, so that's the visual cue. That's what you're looking for is, okay, and here, this is probably NaOH, right? So I'll just have Na plus here. All right, so basically that's what's happening, okay? And all right, so then these become more polar. They will go into the aqueous phase, okay? And then whatever other compound is there, if it's got a lot of nonpolar features, then it'll stay in the organic phase. And now you have a nice separation. Okay, and that also helps you predict which compound is in which layer. Okay, so the charge causes these to be in the water layer because of the strong ion dipole forces with water. Okay, so I'll just draw that in. You guys could probably picture water, you know, bonding to these charged pieces here. Okay, so these are the attractions to water that might form and help it dissolve. All right, okay, so the reason why I'm walking through all this is because you need to detail to me a separation and purification scheme for how to separate 3 compounds. And you need to use these ideas at both a theoretical level and also a hands-on practical level. Like, what's the procedure? You want me to mix this with what solvent? How much of it would you use? When do I do the filtration? What compound is the precipitate? You need to sort of walk through like a theoretical example of that. And then if we were in the lab, you would then use that procedure to do the lab and see how successful you are. So you will have 3 compounds in your mixture, and I will assign you each a specific one. And then you will design sort of a process where you use both of these techniques together in order to separate the 3 compounds from each other. And you would submit to me 2 of those samples, and you tell me what they were. So at the end, you need to tell me what sample do you have at the end of this procedure, and then you do what to it, and then how do you get that second sample, and what is that second sample? Any questions on the objective that I just detailed now? Okay, so that's the basic idea. I have an assignment for you to sort of talk about here. Let's pull that up, okay? So where is it? Okay, let me look for it real quick. I have a couple of things actually. Number one is I've got a theoretical version of, let's do a practice problem together. Here it is. So in the pre-lab assignment, And some of you have probably looked at it and finished it, and others of you maybe haven't gotten to it at all yet. So these are some of the questions that we just covered. You should be able to answer those. Why would you use extraction to separate these three from each other instead of recrystallization? So how do we know these can be separated by extraction? So does anyone have ideas on what it is we're exactly looking at to know if extraction is appropriate?
Since both of them have like a polar part and no polar part, maybe that's why.
Okay, so we have intermediately polar molecules that have so similar polarity.
Yes.
Okay, there's something else too.
Solubility, is it?
Can't two of them hydrogen bond?
It's
But one
more
of
than
them
just
can't?
hydrogen bonding.
Benzoic acid, you can deprotonate, and then
Yes.
aniline, you can protonate. So then they
May-
would be in the aqueous layer, and then benzoyl in the organic.
Exactly, right, Tony. So what we're looking for, if you remember, is this, the functional groups carboxylic acid, make a note to yourself. If you have a carboxylic acid, you can deprotonate it and make it more polar. That makes it polar enough that it'll go in the water layer. Same thing with the amine. You're looking for an amine. If the amine is present, you can make a protonated amine, which is going to be dissolved in water, despite the nonpolar side chains here. Okay, so very good, very good. So right here, I would add an acid because I have the amine, and then that will go in the aqueous layer. And then over here, I have an acid, I would add a base to it, and then that would go in the aqueous layer. And then I would be left with benzyl in the organic layer. Okay. All right, so that's, and there's a flow chart of that in experiment 4. There's a flow chart in part D of experiment 4 that sort of shows you how you would do this stepwise. Maybe you'd add the acid, get rid of this, add a base, get rid of that, and then you have this left over.
Jenny, I have a question.
Yes.
So I think for one of the questions I drew sort of like what I think would be happening.
Mhm.
And on the bottom layer, I thought that I would have the benzoic acid and the nitroaniline. And then in the end, on the top layer, I would have the benzyl. That's why it's the last thing that I would end up with. But
Oh, okay.
but then we were talking earlier today how that's not true.
Okay, so when you say the bottom layer, it really depends on what solvent you're using.
Mm-hmm.
So you can't say top or bottom unless you say what solvent it is.
Okay.
What solvent were you using? Or were you just saying that they would be in different layers?
Well, yeah, but I also said that I would use the solvent. 1 second.
Okay, sure.
So for looks like I'm using different solvents, but for benzyl, I was using acetone.
Mm-hmm. Okay. So acetone is not a good solvent for extraction. Does anyone know why it would not be so great?
Doesn't the acetone bond with itself in water or something like that?
Yeah,
Or am
acetone
I-
bonds with water, and it just would not give you 2 layers is all. You need a more extreme pairing. You need something that's really polar like water and something that's really non-polar like methylene chloride or ether is usually used. Okay, so you have these 3 compounds. And so anyone figure out what could the first step be?
Yes, you dissolve it in diethyl ether.
Okay, diethyl ether. And that dissolves all 3 solids. So you get a vial of 3 solids mixed together, dissolve everything in diethyl ether. Very good. And then what could be next?
You add NaOH to charge the benzoic acid, like you were explaining before.
Oh yeah, exactly. Right. Very good. Sorry. So that's not charged yet. Right. I'm going to add NaOH, and that's going to make this charged. And what layer will this be in?
The aqueous layer.
Right. So this will be in the aqueous layer. And that water comes from aqueous NaOH. Okay, and then the diethyl ether. Oh, sorry, go ahead.
How do you know when you charge the acid that you have or the base that you have? Which one you charge first?
It doesn't matter. I could have added HCl first.
Okay.
Okay, so in the leftover then are these two compounds, the benzyl and the nitroaniline. Okay, so now how do I separate? And this part I probably don't care about, but what if that was one of the compounds I wanted to recover? What would I do to recover this if that's one of my goals? It's in the water layer.
Add more NaOH, is it?
No, this is gone now.
Add
It
acid?
reacted with NaOH. Yeah, that's right, Katyin. Right. I want to use acid and then protonate it. Okay, so I'm going to need to neutralize this conjugate base back into its acid form. And that will separate it from its aqueous layer. It will precipitate because it will no longer be polar enough to dissolve in water to any great extent. It will still, some amount will be dissolved in water, but less so. So then you would dry that, you would dry it, and then you would evaporate the solvent, and then you would have a more pure precipitate there. Okay, so then over here, how would I separate these two? This is where I would add, what should I add here?
Acid.
Acid, thank you. Yeah, exactly. This is going to grab my acid, and then that's going to get protonated and turn into,
the aqueous layer.
yes, very good. Okay, so this is going to be my aqueous layer, NH3 plus now, and Cl counter ion. And then again, same thing, I would dry this, or wait, no, I'm not done yet, right? This is going to stay in the aqueous layer. And some people ask, well, couldn't I just filter it at that point? But no, it's dissolved in the aqueous layer. Some people would boil the water, but water is really hard to boil off. But you could try to boil off the water and everything left would be this salt. But to make it a little bit easier, I would neutralize it. How could I neutralize this?
With a base,
Yeah, very good. What kind of base would you add?
NaOH.
Very good. So I would add NaOH and I would take that H off. And so it sounds like a lot of back and forth, but now it would be in the organic, well, it would be in water. This is not as soluble. So it would precipitate and then you would evaporate it.
Oh, I see what's happening. So the way I think that this is going is, so first you dissolve it in ether so that you can mix them together.
Mm-hmm.
And then for the benzoic acid, you have to charge it so that it's soluble in water, like you were explaining before. So that, because it's an acid, we're using a base to charge it.
Exactly.
And then we need to bring it back to the uncharged form again.
Yes.
So that's why we use a base again to go back.
An acid in this case and a base in this case, yes.
Okay.
It's confusing because you have acid and base. And yes, it will precipitate in water, which is what it's in at this point. It's in water and it becomes more nonpolar. So it will start precipitating white powder everywhere in your test tube. And then another thing I would say is this is diethyl ether versus water. So what's in the top layer and what's in the bottom layer? So we have diethyl ether. This stuff will be in your top or your bottom? Does anyone know? Diethyl ether versus water.
Water will be.
You said earlier that diethyl ether
Yeah,
was lighter than the water, so it'll be in top.
That's right. So diethyl ether is less dense than water. Water is more dense than ether. And so bottom layer, top and bottom layer. Yeah. And then again here, I'll have diethyl ether here. I'll have aqueous here. Again, this will be the bottom layer. So it's good for you to specify because when you're doing a procedure, you would like to know, wouldn't you? Which layer is where, which layer do I remove, and what do I do to it? So these are the kinds of details that you should be thinking about when you write your procedure. Okay, and make it clear to me that you know how to do that. Okay, whoo. All right, any questions? So if you can do this, then all you have to do at this point is just add the details. Like, well, how much of the compound should I use? And that's not so, I mean, that's not as big a deal as just the concept. I mean, if you understand this page as it is, that's great. That's like 90% of it to me. But then again, if you're writing a procedure, then you want to follow some of the amounts that are in your previous experiments. Maybe think about, okay, I would take this many grams and I would add this much solvent. You know, so if you know those things, you can add them in, but some of it is trial and error too. So I understand that. All right, so, but the book says here, it says, the first step in your procedure should be to dissolve about 0.5 grams of the mixture in a minimum amount of diethyl ether or methylene chloride. So they're sort of telling you already what you should be doing. And then they're building into your procedure. If more than about 4 mils of solvent is required, you should use another solvent. So what they're saying is you don't even know if diethyl ether will be the best solvent to dissolve all these. So you have to test it out first. So maybe you start by saying, okay, try testing these out in diethyl ether. If that doesn't dissolve everything very well, then try what? Maybe methylene chloride. And so you can build into your procedure some of that uncertainty and what you would do. Okay, so it's okay not to know how much of things to use or whether this is the right solvent, but as long as you're aware of it, write it into your procedure, because really treat this as you are going to do it next week, okay? Because you would be, if we were on campus, you would be doing this in the lab. So yeah, write it as if you are going to do it, okay?
Jenny,
Yes.
do we have to purify what we get in the end?
Oh, in the end, yeah, you want to provide for me at least 2 of the 3 compounds. And so probably I would choose this one maybe because it's in the organic layer and I can just dry it with Na2SO4, sodium sulfate, and I can evaporate it. And then I should have the pure compound. So the organic stuff, the most organic stuff, is sort of already pretty dry. You've removed all the water from it. You just dry it and you evaporate. So I think that would be pretty good stuff to have. And then you could say in one of my other vials, I would just submit maybe this one, and I would look up the melting point and I would say, okay, so I'm going to choose this one to submit, and the melting point should be 122. Okay, degrees Celsius. So you could just pick one or the other, or you could say, well, I can separate all 3 of them, but you probably would run out of time because you would have the step of neutralizing it and drying it, and that adds time. So you just pick you just pick 2 out of the 3 to hand to me, and you tell me what you would do to confirm. And I will tell you that you can also use IR to confirm what you have. So I would ask you, okay, which 2 compounds in the end would you give me? And how would you know that those were the compounds you gave me? So of course you could talk about melting point, look up the melting point, tell me what it would be, and then think about the IR and tell me what signals you would see in the IR to confirm. So this is purely done on paper. There's no lab work that you're going to be able to do. So keep that in mind when you're writing this out, that it's all predictive, but you do want to add as much detail as you can about what it is that you would see and what would you do to get the separation. All right. Any other questions? So that sounds like a lot, but the basic idea is just this. You're going to use a combination of, well, this is just extraction right here. But let's say for recrystallization, maybe you have 1 acid or base, so you do the extraction, and then maybe you have a nonpolar, 2 nonpolar, and maybe extraction won't work to separate those, so then you have to use recrystallization. Okay, all right. And then this is sort of another question. Recrystallization is better than extraction, probably for, you know, the kinds of things we were talking about. These are pretty nonpolar. These parts are polar, so they're both intermediately polar. It would be hard to separate by extraction because neither one is an acid or base. Okay, so just to sum up what I said, you want to use extraction if you have an amine or carboxylic acid. If you have a neutral organic that's intermediately polar, probably best to use recrystallization.